source. Okay. So we left with what? dE. Okay, let's change the color. So you see how I am applying this control volume approach. If anyone has any problem, you can interrupt me. Okay. So there is only exit. So the only term which survive is this and the enthalpy at exit, right? Because since m dot I is 0, everything in the bracket multiplied by 0 is 0. There is no Q, there is no work transfer. So the equation which we have is dE by dt is equal to minus m dot E He. Okay. What other equation we have? Which balance? So we have done energy balance, right? What else we have?
Mass balance.
Mass balance. Very good. So let's write down mass balance. Mass balance we have dm by dt, which you know always inlet minus outlet. The rate of change of mass in this control volume is at what rate mass is entering and at what rate mass is leaving. So mi dot minus me dot, but we know this is 0. Okay. So dm is equal to simply minus me dot dt integral 0 to t, right? At 0, what will we will take the mass? The initial mass of the gas in the tank. And this is after discharging, partially, fully, whatever. It can be 0 or I will take it mf. So which one is greater, m naught or mf? Which one is greater?
M naught. M naught.
M naught, right? Yeah. So just not very trivial thing, but sometimes we will miss. So m naught is greater than mf this time. So if we'll take this minus sign here, this side, what we'll get is mf minus m naught. Sorry, m naught minus mf, right? M naught minus mf is equal to me dot. Yeah, so or let it be like this, that's fine. So what we are getting is mf minus m naught is equal to minus of me dot dt from 0 to t. This is from mass balance. Okay. Now let's talk about this equation here again. Now again let's integrate it. So d of E is equal to minus m dot E He dt, and then integration 0 to t, and at 0 we have energy, let's say E naught, means in the beginning, and the final energy of the CV is EF. This is all about CV, this fixed region in the space. That's what we do in CV. Okay, fine. He is a constant because this is the enthalpy at the exit. So there will be some pressure temperature condition at the exit. So this is He. Okay. So, by the way, He is what? He is nothing but for a given instant the enthalpy of the gas in the tank, right? Because gas is coming from the tank, right? So He is nothing but H in general is enthalpy
U plus PV.
Yeah, enthalpy, just enthalpy of gas inside the tank at any instant. Inside the tank at any instant. Okay. Great. Which will change, of course, with time. Okay. So now here is a catch. Yeah, I think here is a catch, or just a moment. Can we take this He out? Because He is also a function of time, according to me. I may make a mistake, so I'm just thinking. What do you guys think? Can we take He out? It depends on the problem statement. Otherwise, this is the more general equation. let me see one problem on this discharging, and then probably it will be more clear. So just let me see through problems. Okay. Let me find one problem on discharging of a tank, and then it will be more clear if I can find. Because this HE, I'm not sure which HE we should take. Whether it depends on the external temperature condition or what. So without seeing it carefully, it will not be wise to comment. So I'm just trying to see that. Yeah, so that, that's what written here, what I'm saying. But I'm looking for a numerical problem. Okay. Give me a moment, guys. Oh, yes. So what I'm saying, it seems right. Yeah.
Excuse me, sir.
Yeah, please. Yes.
Sir, He is the enthalpy of gas which is leaving the tank, right?
True.
Then why did you write enthalpy of gas inside the tank?
Yeah, but then what enthalpy will take, right? The gas which is inside the tank, that is leaving the tank, right? Don't you think so?
But but
Whatever you have at a given instant, that enthalpy, with that enthalpy, gas will leave the tank, isn't it? Yeah.
okay.
Yeah, anyway, I mean, you can correct me, or if you can contradict me. What do you think? That's what I think. That the gas will leave with some enthalpy which is there at that time, right?
Sir, but if we control the enthalpy of gas which is getting out of the tank, then we can take He out of the integration.
No, that's the whole confusion. That's the whole point of confusion. That's what I'm saying. That should be made very clear in the problem, that the exit gas you are maintaining at some other given environmental condition, or you are taking the condition inside the tank. That's what I'm saying. Same point, what you are saying. If it is not
Okay.
written in the problem, and if only the conditions inside the tank is given, in that, I think that, not I think I'm quite sure that we should take He is the enthalpy. Let's say after 1 hour. So after 1 hour, whatever will the enthalpy of the gas, with that enthalpy gas will exit, right? See, if you see the mass
Yes.
balance, you remember that we don't care what is outside. All we care about is that whatever is exiting from that control volume, what is the properties of that thing. So that is another case which you are saying. I'm not denying that. That the way we do in throttling, that one can maintain some condition at the outlet, right? But that is not the case in general. For example, I can see a problem here, and this is the discharging of a tank of ideal gas, right? And here, while solving, they have taken H equal to CPT, right? And then they are taking it as a function of time. So that's why I am a bit hesitant in saying H is constant. Okay. Although if you'll see the derivation in the textbook, they have taken it constant, but I am not convinced with this idea, to be very frank. I don't think so. At how one can take this as a constant. So this is the point of confusion, and according to me, so if so if you see in the books, in standard books, they have taken He out without saying anything. On the other hand, when you will see that there in some books they have solved this problem for a ideal gas, they have taken H equal to CPT, where T is the function of time, and then they have used this kind of unsteady state means temperature is inside the integral differential. So let's see. Right now we'll leave it here, and what final equation we can write? EF minus E naught is equal to, I will leave it like this because I'm not convinced with this idea that He is constant. If H is not constant, you cannot take it out of the integral. That is my understanding, say, still. Okay. Later on, if I will be proven wrong, that's fine. But right now, that's what I can think. I will not follow the what is written in textbooks. I will follow my intuition and my understanding. So that's where we are. Still, we haven't used this because I don't see any this how we'll use this. So let's see where it will lead to. According to me, okay, what is EF by the way? So let's solve it further. So EF is what? Anyone? So EF is nothing but yeah, MF, UF, right? And E naught is what? M naught U naught. So that is there is no confusion here. So we know all the terms. Our might only not confusion, but I'm sure that I according to the if you use the maths, I will never take T out, He out, because ultimately it's the enthalpy of the gas which is exiting, and that is varying with time. It's not constant. Okay. So let's say this is our master equation. So if I write it, okay, where is our presentation? So if I write it, what is our final equation? Our final equation is what is happening? So our final equation is MF UF minus M naught U naught is equal to minus of HE ME dot dt. That's what I know till the point 0 to till this point. That's what I know. Okay. Now let's solve it for an ideal gas case, and then I'll tell you why I said it. Okay. And that is a standard problem for solving it for ideal gas, and that answer you can find out anywhere. And then you will see that why I was hesitant to take this HE out, because I think it's a function of time. So if we'll do for an ideal gas, okay, then we all know that for an ideal gas we can write H equals to CPT, right? Specific enthalpy. Huh? And U we can write what? Anyone? CVT, right? That you know already. So if I plug it here, then what I will get? MF CV T final, right? Minus M naught CV T initial, which is known generally, okay, is equal to minus 0 to T. HP is what? CPT, right? And ME dot is nothing but anyone. Minus of ME dot is what? From the mass balance. Remember, dm by dt is minus ME dot, right? So if we write here, it's dm by dt. It's I think we can do, right? No. Okay. Let's see what we can do. Now, if we want to move further, then what we should do from here? This is CPT, and then we have this ME dot dt. So we can write minus 0 to T CPT. The problem is this is also the function of time. ME dot is okay. Let's follow. If we take this one, let's say here we have to do some maths here. So dm by dt is equal to minus ME dot, okay, and if I multiply it with CPT on both sides, that which I can do between 2T both sides, okay, and then if I take integral, then let's see what we'll get. Okay, so what I'm doing here is as follows. Let's do it properly here with some different color, and we'll see what can be done. So we have dm by dt is equal to minus me dot. Now here the term which you want to produce is Cp into T and this, okay? So Cp T, Cp T, okay? And then we have, and if we integrate it, so basically we can write first of all dm Cp T is equal to minus m dot E Cp T dt. Up to this point I don't find I don't think there is any mistake up to this point. If there is any, please point out. Up to this point I think I will fine. Then I integrate it 0 to T, and this will go from 0 to, okay. Here what we'll do, we'll put limit later on. But what do you think? What about this integral? Anyone who is very good in maths? What we should do? Here I think if we can, I think we have to go now in this integral, and I think you will be convinced also. MCPT, right? What we can write this? D of MCPT. Anyone? Snake to try, because here mathematics will be a bit complex, not so straightforward. So what do you think?
So actually CP is
Yeah.
also a function of M, so we can write CP in terms of M, then can integrate.
No, I'm saying just no. Take it specific. Don't make it that thing. Capacity. You are saying heat capacity, right?
Yes, sir.
No. I mean that will extra complexity. What we can do, Sunay, that we can always write it this way, na? Let's say this is if you take in two parts this
Yes, sir.
differential. What we can write?
Yes, sir.
CPT dm, right?
Yes,
That's
sir.
what we want here. Plus this will be m d of CPT, right? That's fine. We know the master equation. Ultimately, we are struggling with math. That's fine. Let's see. Okay, so this, it means, and if I take integral of this, okay, so this I can write, okay, so now this will, so this, if I take integration now, what will happen? So this is fine. This I can always calculate. There is no problem. This value I want. So the main problem is here. What I will write this term if I integrate it. M dot E is fixed. So there is no, wait. If I take M outside of this integration, what do you mean by M? No, it's not so straight. Okay, I think I have to relook this problem, because here maths is not so simple. Okay, but I'm completely convinced that taking HA out is not a I mean it's not possible mathematically. So you remember this master equation, and I'll get back to the solution. Okay.
Actually, sir, if we know that how the temperature is varying at exit condition with respect to time, then it can be like a
No, I
simple.
think that should. I think that is the question which is being which should be asked. That if gas is discharging, determine that how temperature will vary with time. That's what we are asking actually. So if you want to frame a problem, that is a problem. That I have told you the initial condition of the gas. Now it is getting discharged. Okay. So tell me how temperature will vary. Then someone can ask. Okay. So let me think for 1 minute if I can find out the answer. Otherwise, we will move and I will come back with this answer in the next class. Give me a moment. Or rather than why we are going to integral, if we remain, if we just confine ourselves in the differential itself. Okay, I have a new idea. Let's see. What I'll do, that rather than going into, so all these terms getting cancelled, just remove this gone, this gone, this gone. So what is our equation? Just write, let's do like this way. dE by dt is simply minus m dot E He. Okay, let's say I say this. Okay, and if I am solving it for ideal gas, so dE by dt will be what? Minus me dot Cpt. You can find up to this point. Okay, let's say this, and then E I can write what? E is what? Energy of Cv at any time t. What we should write it? If we write it in terms of differential, so rather than taking it, keep it as a differential equation. What we can write? Anyone? E is equal to
CVT.
mu, right? M is the mass at any instant t. So at any instant t, the general quantity is as this: m u h, pressure P. Okay. And P naught and PF, M naught, MF, these all naught and F are initial and final quantities. That's what we can write. So this is fixed, no doubt, but this is a function of temperature. Cp of a gas is fixed because it's a ideal gas. Okay. Then what? So this we have written. Now what we'll do? So we have. Okay. Now what we are. Yeah, please. Yes.
We can write U in terms of CV.
Yes, we can write. Well, let's do it. Why not? Of course. That's what I was going to do. So CVT, yes, perfect. CV will come out. Let's send it here. Okay, perfect. So D of mt by dt is equal to minus m dot E gamma t. Okay. Fine. Now what we can write? This we can write as m dt by dt plus t dm by dt. Now our life will be easy. I unnecessarily went to, but that thing is sure that if you find it in the book that they have taken He as a constant, that is wrong. You cannot do that because He is nothing but the enthalpy of a gas at given instant, and that is changing. So how it can be taken out of the integration? Okay. So here up to this point there is no confusion. Fine. Okay. So then what else? dm by dt we know, right? dm by dt is minus me dot. Okay. Great. So if we will arrange it, next page, and okay, let's make a line here and then here, here. So now if we'll write it, what we'll write? Let's see another color. M dt by dt is equal to, this will go this will go another side. So what we can take common is
M
minus, minus me dot common. Okay, thank you. And then we have t gamma plus 1 or minus 1? Plus 1, right?
gamma minus 1. Gamma minus 1.
No, this is plus, right? So in that side, if I take this term that side, oh, there is one minus again. Okay, right,
Yes.
right, you're right. So this is basically plus me dot. What it was? Come again. Which term, into what? What
T.
was here?
T.
Yeah, T. Perfect. Thank you. Yes. So T. Good. So then we are taking T out, and then we have 1 minus gamma. Fine. Okay. Thank you. Great. Okay. Yeah. So
How much, sir, remove the outer minus?
outer minus will be removed.
Like minusing with respect
Oh
to
yeah,
M.
yeah. Because you have taken either one. Fine, fine. Now what about m dt by dt? What we are going to do with this, that we have to see. This is fine. Okay, now we have to solve this integral. So how we are going to deal with this? Do we have any dm? Okay, life is easy. So we can write m dot t as dm by dt, right? Yeah. Now it's in line. Okay, fine. So up to this point it's fine. Then m dt by dt is equal to, this is nothing but dm by dt with minus sign, right? Yeah, with minus sign. So again one minus will come. So this minus can be absorbed inside, and then it will be t gamma minus 1. Is it fine, Bhavna, Sneh, up to this point? No mistake?
Yes,
Okay,
sir.
great. Then dt dt get cancelled. Yeah. Now we'll integrate it. So it will be dm by m and dt by t. Okay, next page. Or we can do it, we should do it here itself so that you can follow. Dm by m is equal to dm by m, I think gamma minus 1 will be, so let gamma minus 1 dm by m is equal to dt by t. Perfect. Okay, so in form of differential equation, life is easier. So this is ln and this is here also ln. Okay, let's go to next page. So we have gamma minus 1 ln mf by m naught, and there is no minus sign problem. Okay, fine, no problem. So then next page is equal to ln tf by t naught. Fine. So this will go as exponent here, gamma minus 1. Okay. So if you want to find out the final temperature, this will be simply Tf by T naught is equal to Mf by M naught gamma minus 1. Okay. So Sneh, now you got the point that that's what should be asked, that how temperature is varying. Like this is the when you say Tf is function of what? Mf, right? And Mf is function of what? The rate at which this tank is evacuating, right? You got the point?
Sir, I
Yes.
have only one doubt.
Yeah, please come. Yes.
Sir, while this obtaining this differential equation,
Yeah.
and while it, like we have written H as CPT, and
Yes.
on the left
HCP.
side we have written E as CVT. But sir, these
Yes.
both T are different, no?
No.
One T is for the electron volume, and one
No.
T is for gas exiting.
No, that's what I'm saying. That's where the confusion. There should not be any confusion. Let's see, whatever gas. Okay, let's make it very clear. Huh? Whatever gas you have here, right? At any instant, that same gas is living, right? You convince
Yes.
me. So, same H is everywhere, right? All the gas properties are same at a given instant. Either it's exiting or it's sitting here, anywhere in this CV. If you see the balance, this energy balance, we write the property of fluid which is coming out of the CV, but that property is linked with CV. Okay.
Okay,
It's not
sir.
the outer condition, and that's why we can write it. That's the whole point I'm saying. That if if you will say that H is a different condition, then it can be treated as a constant, and that's why I say that it's not correct. It's wrong. H is nothing but the H at that given instant of time. You agree, or otherwise I can elaborate more?
Yes, sir.
Yeah, because gas is exit. So let's say you started with some T naught, P naught, M naught, and of course whatever it is, and H naught. Then evacuation starts taking place. At any time t, your mass will, at any instant of time, you have some mass, you have some pressure, you have some temperature, you have some U, and you have some H. And this is valid throughout this CV, either exit or here, doesn't matter. Exit is also the part of CV. And that's why we can write this H as CPT and this E as empty, because E is nothing but only consists internal energy, U. Okay, and that's why this T is same.
Sir,
Yeah, please. Yes.
sir, why we are taking m outside of bracket in third equation?
In
D
third equation. Here?
mt by dt.
Oh, no. We have difference. Okay. I think you missed one step. Who is it? Just tell me the name.
Nidhi.
Nidhi, you see, let's do it in front of you. Okay. I am omitting these terms. Okay, now you differentiate this dmt by dt. You missed one step, that's why you are confused. Tell me, Nidhi, what will write? M
dt by dt
plus T dm by dt.
dm by dt.
Right? Now what is dm
Yes.
by dt? Minus me dot.
minus m. Okay, sir.
So
Yes, sir.
I have taken it on the right hand side, and that's why you are getting m. I'm not. I'm just following maths, right? Clear?
Yes, sir. Now it is
Okay.
clear.
Yeah. Fine. Great.
Hello, sir.
So yes, please. Huh?
Sir, can you go to the last equation, like the final answer that we got, like
Yeah,
TF by
sure.
T?
Yes, yes. I am going. Just let me write this down. Sure. Last page. Yeah, here. Yeah.
Yes, sir.
Image.
So here, MF is a constant, right?
No. No. Why MF is constant?
Sir, we have taken
Depends on, you see, it depends on problem that for after how much time you are asking me that what will be the final mass. Final means your final time. It can be 1 hour, 2 hour. It depends on the. I mean, it can be until the whole gas goes out. MF can be anything, right? It depends on the problem. Whoever is asking the problem. Like, let's say if I say that there is a tank, okay, and let's say there is 5 kg gas in that tank. And if I'll ask you that, let's say that when half of the tank will be, what we say, half of the tank will be evacuated, what will be the final temperature? Or I can ask you, what will the final temperature when 3/4 of the tank will be evacuated? So how MF is constant? MF is the final value which user will set, or which the person will set who is setting the problem, isn't it?
okay, sir.
Got the point? So basically MF, see, ultimately remember, we know that dm by dt is minus me dot. Let's say if I tell you that me dot is 2 kg per second, and if you run, and let's say your total gas filled is 10 kg m naught. If you run this operation for 2 hours, sorry, 2 kg per hour, let's say. If you run this operation for 2 hours, how much gas has gone out? Yeah, who asked this question? Just answer. How much gas has been gone out? 4 kg, right?
Yes.
So your MF will be 6 kg. But if I ask you the same problem after 3 hours, then how much gas has gone out? 6 kg. So your MF will be 4 kg. Okay. So everything is changing. Final mass depends on what is your final time. 1 hour, 2 hour, 3 hour, or complete evacuation. In case of complete evacuation, MF will be 0. And that's all. But I don't think for MF 0 we can do anything. Nothing. Okay. And that is an impractical problem that it really completely, creating vacuum is a different thing. We are talking a problem where gas is naturally going out. We are not pulling it, right? So is it clear up to this point? So we should, and that's why I say, someone said that why don't you take He constant? Your name, please. Or I think we discussed already with, who was it? Just to make sure that you got the point that H is not constant. And that's why whatever written in the textbook, that is wrong. Yeah, anyone, who was that person? Who suggested that H should be constant? Okay, no problem. Anyway, so we have already proven that this should be our, either you take, so basically if you want to write down the master equation, very simple. Either you keep it in a differential form. So we can simply write this way, that the master equation should be, for discharging, simply.
Sir,
Yes, please.
for this H equal to CPT and U equal to CVT, this we can write only for ideal gas.
Only for ideal gas. Otherwise, other details has to be given. Yes. Or H should be known as a function of time. Yes,
Okay.
true. It's not a general case.
In
So I'm
the
writing.
last integration step, we are taking gamma as a constant. So gamma is not varying with the mass.
Because we are taking ideal gas.
Okay.
Gamma is nothing but CQ by CV, right? For
Ideal
ideal gas, CQ and CV is a property of a gas rather than mass, right? Or rather than pressure and temperature. It's independent of everything, the state variables.
Okay. So for real gas, we cannot take it as constant.
No, not at all. Then this problem will be more difficult. So that's why finally I'm writing the final equation in 2 formats, and then further information is needed to solve the more real problem. Yes, you are right.
Okay.
Just in order to remove any confusion, the more general equation will be d of mu by dt is equal to minus m dot e he. Either you keep it in this differential form, and then remember, there should not be any doubt that this HE is function of time. There is no doubt about it, because HE is nothing but enthalpy of gas in tank at time t, because you are writing this differential equation at time t. Okay, so there shouldn't be any confusion, which is nothing but the gas of the tank, or CV, you can say, same thing. Okay, so that is that's how we solved ideal gas from the differential equation. If you want to like go one step further, you can always write MFUF minus M naught U naught is equal to minus of M dot E HE dt. But be careful, you cannot take it out. Rather than HE, you can simply write it H, because H is a function of time, whatever you want. Okay. Yeah, so that's the overall story. That don't take H out. So unless and until you don't know how H is varying with time, there is no other way. Okay, now I have a quick question for you, and a bit innovative. That if I tell you that how pressure is going to vary, okay, if I'll tell you, let's say 10 data points at different time, or basically you can say that if I give you, let's say this operation goes from 0 to 1 hour, and after each minute I give you 60 points, and I tell you the H. So I tell you HE at different time. Okay, so 0, then 1 minute, 10 seconds, 20 seconds, and so on, up to, oh no, 1 minute I said, so 60 seconds, 120 seconds, and so on. So how you will solve this problem? Anyone? So have you done numerical methods? Still, you would have done it, right? Numerical integration in any course that your maths course is going, na? There, I think you will cover this numerical integration. Have you heard this term ever? That how we can integrate numerically?
Polynomial expression.
No, not binomial. No.
Sir, using trapezoidal and
yeah, using
1/3
trapezoidal. Yes,
circle.
exactly. So that is the only way there. If it is for a real life problem, you have to tell me that H as a function of time, or in other words, for each instant of time, the state property should be known. Then only we can solve it. Okay. So don't follow the textbook. It's wrong there. Taking HE out is completely wrong. Okay. Great. Fine. So discharging of tank is done. Now we go to another interesting problem. Since I promised that today we'll only solve problems, so that you can, it's always easy to understand, and it's always good to go through problems. Then only you realize that where is the mistake in your concepts and all of such things. If you only do theory and if you don't implement it, you will make mistake, that's for sure. Okay. So this problem here, what is happening? A thermally insulated empty tank, and after this we will stop. Okay, so we will start fresh this thing, that second law from the next class. So we have thermally insulated empty tank which contains a spring piston arrangement. You can see here as shown in figure 1 below. This tank is connected with a supply line containing steam at pressure equal to 2 megapascal and temperature 300 degrees Celsius. So supply line properties are fixed. So this is kind of charging a cylinder, but this time, okay, and here we are maintaining vacuum. Okay, so this is vacuum. So here maintaining vacuum, and so then you can open this wall. Okay, initially the spring is just touching the piston. So initially spring is just touching the piston. Okay, there is vacuum and this valve is closed initially. No extension, no compression, and valve is closed. So this is stage 1. In stage 1, there is nothing in this tank. Okay. Now the valve is opened. So you open the valve. So valve is opened, and steam enters in the tank till the pressure inside the tank below piston. So means here pressure, final pressure becomes equal to 2 megapascal. So gradually gas is entering. So it is a charging problem, no doubt. But what is happening here? We have this extra arrangement. This is spring. Okay. So question has been asked. Express the enthalpy of the steam in the supply line in terms of final pressure, final specific volume, and final specific internal energy of the gas inside the tank. So you have to express, say it HS. You have to express HS in terms of EF, UF, VF of gas in tank. That has been asked. What is the relation between them? Okay, fine. So let's do solve this. So what we are going to do is that let's say that first we consider our system. First we consider our system as gas below piston. Gas below piston. This is our system. Okay. Fine. So can anyone tell me that when I say gas below piston, it is a control volume problem or control mass problem?
Control mass.
Control
Control
mass.
mass.
No, 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 no. If you take the cylinder only means I'm not taking the supply line. So gradually the mass in the tank below the piston will increase, right? Don't you think so? Isn't it? Think over it. So it's not a control mass problem. Anyone has any doubt? Anyone want to contradict me? Since the mass below the piston inside the tank will increase with time, it's not a control mass problem. It's a control volume problem, but this time the envelope of control volume is changing. So we cannot say it's a control volume problem also, frankly, because generally we say that in control volume is the region fixed in the space. So I don't know which definition we should follow, but certainly this is not a problem of control mass. With the way I have taken the system, you are free to take the system the way we did it earlier, that you have to take some gas in the supply line. So you are free to do that. You'll get the answer. But I am forcing that if I take gas below the piston as my system, this is certainly not control mass. Whether we should say it control volume or not, that's a different question. With the strict definition of control volume, I don't know. But I can solve this problem by taking gas below the piston as my system. Because thermodynamics all demands that define your system. You would be able to solve the problem. So that is my take on this. If anything you want to say, otherwise we'll solve this. So let's see. Okay, if something comes to your mind, you can tell me. Now, since it's a control volume, whatever we want to say, let's apply the first law. Okay, so I'll just copy the first law here so that it will help you. Just keep it in front of us. Okay. And then once we'll write down the final equation, we'll remove this. Okay. So now tell me what term. So yeah, of course there is no exit, right? So exit gone. So if exit gone, this whole thing gone. M dot E is 0 because there is no exit. The lower boundary of my CV is fixed. Okay. Of course, this is the final shape of CV. And in between, how CV will look like? Something like this. In between. Okay. So my CV is growing. Okay. So this is 0. Fine. Ignore the kinetic energy. All kinetic energy, macroscopic. This is gone. No elevation. Means no gravitational potential energy. Okay. So we're left with what? dE by dt is equal to minus m dot I hi. This hi is what? Which hi we should take? From where gas is coming? From supply line, right?
Yes, sir.
So this is
Supply
HS
line.
this time, there is no doubt. Okay. There is no Q dot, no heat transfer, because we are not giving any gas to the heat, any heat to the gas. This is also gone. Now we have to talk about this term. What do you think? W dot shaft. What we should do with this term? Do you think this term will drop, or you have any suggestion? So for this, you think whether
Mainly
your gas is
non-zero
working
cause gas will do some work on
on
spring.
spring, right? That's it. So they don't think that shaft work is always a rotor or a. See, ultimately you have to remember whether your gas is working or not, and that work can be done in any form. I can put a film also, and let's say that film is getting dragged, or that surface tension forces. Here we have a spring. So now we know the more general notion of shaft work. It's not always that turbine is running or some fan is running. Your gas, if it is doing work on external agent, then, and if that you're saying external agent means that is not the part of the system, then in that case, this is W dot shaft is that we have to take that shaft work. Okay. Because remember, enthalpy and energy, this H, this only takes care of the PV work at inlet and outlet. If ever you have confusion, go to the whole derivation of energy equation. The work, you remember that we have considered the work at inlet and outlet only, which take care of pressure volume at inlet and outlet. So we don't need to consider PV work because that is information is already there here in H. If you see the control volume derivation energy equation, you have considered work done at inlet, work done at outlet. That information is in the H. But if there is something extra work done by your system, which is the case here, that our gas is working on the spring, we have to count it here. If you don't want to say it's shaft work, don't say it's shaft work. Say it work done by gas, apart from PV work. So if this is nothing but W by gas, what kind of work? Non-PV work. Means rather than non-PV, you should say non-PV inlet outlet. Non-PV inlet. Okay, let's write it properly. This is W by gas apart from PV work at inlet outlet, apart from that, because that information is hidden in enthalpy. Apart from PV work at inlet and outlet. So if you don't want to say it's shaft work, no problem. You say it's simply work done by gas. Because if gas is working, you have to count for that energy. Okay, fine. Great. So now what we'll do? So now we'll do as follows. Let's say that okay, first what we can do that we can integrate this equation. So if you integrate this equation, this one, let's say this equation 1. So from equation 1, what we can say is as follows. From equation 1, we can say if we integrate it, d of E is equal to HS is supply line property, so HS can come out. Let's say minus is here, and we have mi dot dt integration 0 to t plus ws dot dt 0 to t. So now we'll think about this term one by one. Okay. So if you write d is nothing but EF minus EI. Oh, this will be also integration E naught to EF. Okay.
Excuse me, sir.
Yes, please.
Sir, I did not understand that. Why did you take a minus sign in front of m dot and HS?
Oh, there is a minus sign here. See this one, isn't it?
Where?
Here. This minus sign. No.
What?
So
Got it?
in original equation, it should be plus sign.
Oh, sorry.
Minus sign.
Oh, it is plus now by mistake. Oh, I'm very sorry. Then it's plus. You should have told me. Sorry, I thought it's by mistake. There is no minus. Yes. Oh, I thought there is a minus. There is no minus. Thank you. Yes, you are right. I thought there is a minus. Okay. Since it's an inlet, so it is plus. Very good. True. So there is no minus. Thank you. Okay, fine. So let's move ahead. Mi dot dt. Okay, perfect. What is mass balance, by the way? dm by dt is mi dot. Yeah, so we can write mf minus m naught is mi dot dt 0 to t. Okay, so this is nothing but ef minus e naught is equal to hs supply line m final minus m naught. Now we left with this ws dot dt 0 to t. ef is nothing but mfuf yes, anyone wants to say something? Minus
Excuse me, sir.
yes,
Sir,
please. Yeah,
sir,
please.
there will be, sir, there will be, I think, minus WSDT. Sir, from the original
Yes,
equation.
you are right. There will be minus WSDT. Yes, yes, very good. Just look these things carefully. Huh? Yeah, very good. Wonderful. There should be, because here we have minus. True. Yeah. Right. So it's good to make some mistakes so that students will be attentive. Very good. Minus WS. Thank you. Put a minus sign here. Good. Minus. Great. Very good. So that's a real class when a student is attentive and teacher is not so attentive, so that you can find my mistakes. Okay, good, great. So let's move. So we know all the terms. Now we left with this. This one. This is the work done by the gas on the spring. Okay. So what it will be work done by, let's calculate it. Meanwhile, I'll check that I have done everything fine. I think so. There should not be any problem. Yeah. Wait, let me check. EF, this is fine. EFI is fine. This term is fine. HS MF minus M naught is also fine. Okay. Yeah, I think so. It should be fine. Let's do this. So now, who will help us? So remember, we are now interested in this term. Okay. So work done. So WS dt 0 to t is what? Work done by gas, right? In this time, rate of work done and multiplication the simple, isn't it? Right. So because you are just integrating, there should be some rate of work done on the spring. Why we should care? Ultimately, when we integrate it from 0 to time, it is the total work done by the gas going from starting from time 0 to t. So can anyone help me? What will be work done by gas quickly on spring? On spring, so that we can end the this class in 3-4 minutes.
Half
Yes.
x final square minus x initials.
Yeah, so why don't we go very with a fundamental thing that this will be kx f dx, right? So kx dx 0 to xf, and then we know that we can convert it in terms of this x in terms of volume, right? What do you do that? Kx becomes out to v by a, right? Am I right?
Yes.
A dv. Yeah, so v by a dv 0 to vf, because this time real volume, initial volume is actually 0. So 0 to vf. So k v square, so k by a vf square minus nothing, minus 0. So this is gone. So this k, this is the w by gas on spring. Okay. And if you apply force balance, what we can write? We can write from force balance that yes, anyone from force balance we can write k xf is equal to final pressure F into a, right? Yeah, good. So it means, and if I write xf as vf by a, oh, have I done any mistake? Just check.
So, while changing the limits from 0 to x to 0 to vf,
Yeah,
like
yeah.
the initial is like full volume of the container, right?
No. What is our system?
When x equal to 0, like when there is no compression,
Yes.
then the volume. Okay, okay. Sorry, I
You
got
got the
confused.
point. Huh? My system is below the piston, not up. So no problem at all, right?
Yes, sir.
That's why I said that this time I'm taking system below the
So
piston.
there should be a half under VF.
Oh yeah. Integration was a mistake. Yes, very good. Thank you. And here, help me here also. So K
Sir,
XF is PF
K
into
square.
yes, no, x square by 2, right? So VF square by 2, I think this is fine. Anyway,
Sir,
this
there
math you
should
can do,
be A
but
square.
oh, A square, there is one A here also, D of V by A. Yeah. Okay, A square. Fine. Okay, now it's fine. So here we can write XF as VF by A, PFA. So this will be what? K VF by A square is nothing but PF. So using this to here, what we will get? K VF square by A square is PF. So one VF will be left. So you can write it PF, or just to make it very clear, I am writing it this way: K VF A square. There is a half term, and then this is VF. This will lead to simply K VF A square is nothing but PF VF by 2. So I purposefully expressed work done by gas in terms of final pressure and final specific volume. So we know the work done by gas on spring. Then life is easy. Okay. So now we know this term. So just go back and this term. So ultimately our final thing will be, let me write it for you. Our final thing will be MF UF minus M naught U naught is equal to HS MF minus M naught minus PF VF by 2, because my gas is working a positive, doing a positive work, so there should not be any confusion. Okay, fine. Now that's all. So this is our master equation. Now this simply for this problem M naught is 0 because there was nothing in the system. So what it will lead to if we take M naught 0, what we'll get? Let's do it here itself. If we take M naught 0, then it is MF UF is equal to HS MF for M naught equal to 0. Na? For M naught equal to 0. MF UF HS MF minus PF VF by 2. Okay. So what? Yeah, that's all. We have expressed it. That's what we wanted. Fine. Finish. HS, we already expressed HS in terms of this. What it will be? HS will be okay. So HS will be. Let me open the new page. Just someone can please note down this one, this equation, and tell me what it is. New. I am opening the new page. Just tell me that equation. What it is? MF UF for this case, because here M naught is 0. What is MF UF is equal to?
HS
MF
into
HS. MF into HS minus, right?
Minus.
PF VF by 2. If you take, if you bring this side, this, is there any M missing here? It's fine. I think it's fine. No mistake. Okay. So that's all. If we want to arrange it, can we do something with this? No, I think nothing. So HS will be nothing but MF UF plus PF PF by 2. That was my original question. That express HS in terms of final properties of the gas inside the tank. Okay. So you can do this. And hence, so that the final enthalpy of the steam tank is greater than steam enthalpy in the supply line. So you just try this. This is math.
Sir, it will be divided by MF.
From where? Oh yeah. Oh, where? Have I left something? Should I go to? So one MF is missing here. You are saying here? Is it? Let's go back and point out if there is any mistake. I think it is fine, na? Oh. Okay. You are saying, so if I put MF here, then it's fine. Now it's okay? Now it's okay. So if you are saying, sir, if you want to divide it by MF, then this is MF. I think I have missed something, or is there any calculation mistake, you think? I don't think so. Fine. This is very trivial. I told you that how to solve it. Go ahead with this. I'll give you the final expression. Bhavana, is there any mistake? No? Or it's fine? Is there any MF missing somewhere? Some trivial mistake? Should I go back?
Sir, it is correct.
It is correct. I think there is no mistake. If you see dimensionally, no, I don't think there is any problem. Fine. So don't forget about this. You remember this one, no? And you are smart enough. Why I should do this maths? You can do it. This is your master equation. Means why I should say master equation? This is yes, please.
Sir, in question, it is written hence show that final enthalpy of steam in tank is greater than steam enthalpy in supply line. But from here, steam in supply line is greater than in tank.
Is it? Let's see. Okay, fine. We will do that. If you have time, let's do that. Okay. So this is our equation, and what we are getting is m naught 0, m naught 0. So this is fine, minus pf vf by 2. So final equation is coming out to be HSM. Okay. So let's write it this way. So we will write it HSMF, HSMF is equal to MFUF is equal to UFMF is equal to UFMF plus PFVF by 2. Up to this point, it's fine. Whoever has asked this question. What's your name?
Nidhi.
Nidhi. So up to this point, it's fine. Nah? Okay, now coming to, so we have to prove what? That so hence so that it may be wrong also what I've asked. So let's see. Hence so that enthalpy of steam in tank, so HS we have to show is greater than steam enthalpy in the, sorry, H in tank. Na? So HF is greater than HS. Huh?
Yes, sir.
HF is greater than. Let's see. Okay. So we can write it what? HS MF. If I take MF that side, what we will get? We will get UF plus. Okay. Can anyone tell me with this VF is specific volume or total volume? Okay. Now I got the, you know, that's what that is a missing ingredient. Let's go back. Just okay. Here it you know this VF you haven't said. Yeah, this is V cut. Total, because here if you see that, where is that thing? That slide where we have done some force balance or something. Here you remember this is you are taking this total volume. That was a mistake. Not mistake. We just overlooked this. This is V cut total volume. And what is this total volume by the way? VF is equal to in terms of small VF, MVF, right? MFVF. Don't forget. Now it is. That's why
yes,
that's why many people were. I was also a bit like confused that where that MF is going. It's actually it's total volume. Good. Now there is no confusion. Okay. So now let's go there. Back. Yeah. Okay. Perfect. So UF and this is V cut. So this is PF by 2. V cut F by MF, where V cut F is total final volume of system. Final volume of system. So or gas, whatever. So HS is equal to UF plus PF. Nidhi, what is this? VF by MF? Specific volume, right?
Specific volume.
So VF by 2. HS is equal to, I can write it, UF plus PF VF minus PF VF by 2. I can write it, right? And then HS is equal to, H supply is equal to H final of the tank minus PF VF by 2. Right, Nidhi? Now you see that, yeah, of course, this is a, so you can always write this way, na? HS minus HF. And it is coming out to a what? Negative quantity. So H supply is less than HF. That's why I asked. Right, Nidhi?
Yes.
Yeah, that's all. Okay. And B part, I am leaving it for you. Where you see the steam table, and I've given you the main equation, so it's not difficult. So with this, guys, First law is over. I hope you enjoyed. Second law is more, I mean, it's full of, insights. And we'll try our best first to read the second law from conventional way, a very bookish way. And then I'll take you to completely philosophical way. And then you will appreciate more. Why I'm doing it purposefully, so that we don't miss anything. So let's first follow for first 3-4 classes, very conventional way, like Kelvin's Planck statement, process statement, heat engine, all these things. And then I'll give you the another philosophical insight, and then we'll see all these things, and everything will look same. And just closing statement for today. Remember that second law is nothing but degradation of energy, nothing else. It's all talks about that. What does it mean by degradation of energy? That, see, there is energy, but whether you can use that energy or not, that is the main point. For example, let's say when you are running on the sand, some energy is getting converted, or if you are running your vehicle on the sand, due to the viscous forces or frictional forces, there is a lot of heat generation. So whatever was the kinetic energy, that went to heat energy. But now using that heat energy again in converting that heat energy into work, it's extremely difficult task. Energy has degraded. So kinetic energy has more potential to work, whereas heat energy has less potential to work. So ultimately, second law is nothing but degradation of energy. And second law is a universal truth. You cannot avoid it. That's in nature. With this, we'll meet on Wednesday, guys. Thank you for your time. I don't want to arrange class in the weekend. So let's see next week your maths prof doesn't